Welcome to NeuroRobot Remote Labs from Backyard Brains. My name is Christopher Harris. In this video, I'm going to introduce the NeuroRobot app and discuss brain simulation and designing brains in the app. When you start the app, you get to this interface. There's a drop-down menu here where you can load pre-configured brains, but in this video, I'm going to start a new brain. So I'm just going to give it a name here. And then I click Connect, which is going to connect my computer to my robot's Wi-Fi. This video assumes that you've downloaded and installed MATLAB and the NeuroRobot app, and that you've connected to the Wi-Fi network of your robot. After that, you should be able to click Connect, and then to start the app or to start the simulation of your brain, you click Start. This is the simulation interface. The NeuroRobot app basically does two things. It can simulate brains and it can design brains or allow you to design brains. And this is the simulation part. So once we've designed a brain, it's going to be here in the middle in this brain-shaped workspace. And then there are 13 contact points on the edge of the workspace here that allow you to give the brain input from sensors. This is a distance sensor that tells you how far in front of the robot there's an object. This is the left part of the visual field, the robot camera's visual field, and the right side of the visual field. This is the motor, the left side motor going forward, the motor going backward. There are two motors on each side, but in fact the robot that you're probably using now only has two motorized wheels. And so when you click on one of these, it's going to automatically go to the other one, and you can just ignore the fact that there are two wheels. They do the same thing. There's a microphone here, and this is a speaker, and that's actually it. That's everything there is in terms of the sensory input and the motor output for the robot. You have three input sensors: the distance sensor, the camera sensor, which is divided into two, and the microphone. And then for output, you have the motors on the left side, or the motor on the left side, the motor on the right side, and the speaker. And so in these windows here, you can see what the robot is seeing on the left side of the visual field, the right side of the visual field. You can see what the robot is hearing. So in fact, when I'm speaking, it's picking up kind of increased or enhanced sound at roughly the 500 hertz range. If I whistle, you can see that the microphone is basically tuned to pick up different frequencies of sound. And you can make neurons respond to specific frequencies of sound. Similarly with vision, you can make neurons respond to colors, to shapes, to objects even in the visual field. And then down here you have 5 buttons. The design button takes it to the design mode where we'll go next and actually create a brain. And then in addition you have a save button that saves the current brain, restart button that simply restarts the interface without loading the same brain that you're currently using. The stop interface, which takes you back to the startup screen where you can pick another brain or start a new brain. And a dopamine button that gives the brain a dopamine reward. And we'll talk about what that does later. This is the design interface. This is where you go to create new brains or modify brains, add new functions and circuits to existing brains. And so the easiest way to do this is to just click anywhere within this brain-shaped workspace. What that's going to do is to add a single neuron. You have a number of options here of what kind of neuron you want to simulate, and a confirm button. The way that neurons are simulated in this app is it implements something called an Ishikevich neuron. That's a particular kind of computational neuron model that allows you to reproduce many of the activity patterns of neurons that you see in real brains. So as you know, neurons can be either quiet or active. When they're active, it's also called spiking. They produce these pulses of electricity that travel along the axon and can activate or inhibit or have other effects on neighboring neurons that the spiking neuron is connected to. And so in this case, I'm going to start with a quiet neuron, meaning it has no spontaneous intrinsic spiking activity, or very little. And so I'm just going to hit confirm here, and you'll see that the neuron is positioned in the workspace. Let's add a couple of neurons. I'm then going to add sensory input to these neurons. So if I want to make neuron 1 here respond to the color red appearing in the field of view, then I click first on this little orange rectangle next to the eye, and then on the neuron. And then that produces a drop-down menu here where I can pick from a few different visual categories or visual features that the robot detects. And then so if I wanted to detect red, I just hit confirm. And now you can see there's a synapse going from the eye to this neuron that ends in this red diamond, indicating that whenever there's red in the visual field, this neuron is going to respond. And so I'm going to do the same thing on the other side and have that one respond to red as well. And then I'm going to have one neuron respond to input from the microphone, and let's make it a 700 hertz signal that it wants to see. And then I'm going to create a few axons between these neurons. So if I extend an axon to a neighboring neuron, it's going to ask me to input a synaptic weight here, that's the strength of the synapse, and click confirm. So again, if I want to extend an axon from one neuron to a neighboring neuron, I click on the neuron first, the presynaptic or sending neuron. I extend an axon to the target or postsynaptic neuron, and then I define the type of synapse I want to be using, and we'll come back to this. Let's make this one inhibitory, so let's make this one -40. Okay, so now we have 4 neurons. One is a visual sensory neuron, meaning it responds to red. Another is a auditory sensory neuron, which responds to a particular sound frequency. And that neuron also activates a third neuron and inhibits a fourth neuron. So I'm going to save this and then return to runtime to see what it looks like. So as you can see here, the red neuron or red detecting neuron is being permanently activated by seeing the red here in the image. The sound detecting neuron is basically not active at all, but if I try to whistle at a 700 hertz frequency, you can see that that actually activates that second neuron. And in addition, it activates neuron number 4 because of that excitatory or activating synapse going from 2 to 4. So I'm back in design mode, and I'm now going to add a few different neuron types to show how that works. So if I click within the workspace, I get this list of pre-configured neurons to choose from. And so if I click, for instance, on generate bursts, you'll see that 2 of these parameters down here, the B and C parameter, changed. Each neuron in this simulation is defined by these 4 variables, A, B, C, and D. And if I pick, for instance, bursts when activated, you'll see that C went to -13 and B went to 0.1. If I go back to quiet, you'll see that C changed to -65. If I go to generate bursts, both B and C changed. You don't need to understand right now how these parameters actually work, but what's important to understand is that they generate the different types of neuron that you have available. Different neuron types have different spiking properties. They have different levels of spontaneous activity. They require different amounts of activity to be activated themselves. They respond in different ways to inhibition. They generate longer or shorter bursts of activity when they are activated, and so on. And these are really important properties that make different neuron types within the brain unique. And it's something that's usually not seen in AI systems. They don't have this level of uniqueness at the cell level. And so I'm going to create a few burst generating neurons like this. And then I'm also going to extend an axon from each of those neurons to the speaker and give them each a kind of randomish output. And then we're going to just see what that sounds like. So these are neurons that are going to spontaneously generate bursts of spikes, and that's going to activate the speaker. So let's go back to runtime.